EdExcel P3 chapter review 6, differentiation questions. Question number 9 gives you this function f with e in it. So we have e and we have a trig function sine 2x, which is a double angle function. The restriction to check is that x is between 0 and pi. For this, I just always write 180 underneath it for my own records because I don't like working in radians, but you need to work in radians. Okay. So number A, use calculus. So that means that you're going to get marks, obviously, for every step. You can't just use your calculator to find the coordinates of the turning points of the graph. So turning points, for turning points, our first derivative equals 0 at the turning points. So first thing, find the first derivative, equal it to 0, and that will give us our x's. And then we sub it back into the original curve to get our corresponding y's. So let's go. This is a function times a function, so we're definitely going to be using the product rule. So pick one for u, pick one for v. I'm going to be e2x as my u, and my v will be the sine function. Okay, for u dash, usually if you had an e function, it would be something just ex. Then we know that our first derivative, our dy dx, is just going to be ex. But this is a function inside a function. So this little 2x, you need to then times it by the first derivative of the function inside the function, which in this case, the first derivative of 1x is just 1. But here we'd have to times it by 2 because the first derivative of 2x is just 2. So we end up the same thing, whole thing. Whoops, that's not right. 2x times by the first derivative of the 2x, which is just 2. Okay. Then v dash, first derivative of sine is cos. Oopsie. Same rule or same sort of thinking applies. You can, it's like a version of the chain rule. So you take, if you had sine x was y, then cos, dy dx would be just cos. But since we have a function inside a function, we have y as 2x. So our dy dx will be cos 2x, but we mustn't forget we times it by the first derivative of the function inside, which will just be 2. Okay, so our v dash would be 2 cos 2x, 2 cos 2x. But we're not done. Product rule. Product rule states u dash v plus v dash u. So we first go this way and then we go that way. As I go, I'm going to clean it up a little bit. So we would have 2, this e2x2 is just 2 e2x. So let's just put here, this is, we're doing f dash of x. So 2 e2x times by sine 2x plus, so that was u dash v. Now we're doing v dash u. Let's do 2, and then I'll put the e in the middle. e2x cos 2x. Okay. That should do it. Last step, you just, anything that you can simplify. So let's take out a common factor. So we could take out a common factor of 2e2x. Which is going to leave you with sine 2x plus cos 2x. Okay. Let's leave it like that. Calculus, so A, we haven't quite finished. So we need to find the exact coordinates of the turning point. So we said that this is our f dash of x. And we are doing turning points, and we know that our turning points f dash of x equals 0 because the gradient is 0 at those turning points. So if we had a curve like that, we know that the gradient would be 0 over there at a turning point. Okay. So let's split this up. We can just divide this 2e2x. If we times that by 0, that's gone. So we end up with sine 2x plus cos 2x equal to 0. So what are we aiming for? Doesn't give us anything that we're aiming for. So I always try and put it as 1, either sine or cos. And when I see this, I always think tan, because somehow if we rearrange this, let's take cos over and then divide through by cos, we're going to end up with tan 2x. And it's just, you always want just one sine, cos, or tan. You don't want a whole bunch of big mess. Okay, that's going to be equal to -1. Don't forget the -1 there. Common error, people say 0 for some reason. Just that -1 is still there. Okay, we want the x's. So there's so many methods to do this. Let's first take tan over. So our reference angle, we have 2x is equal to tan to -1 of -1. Which comes to pi over 4. So this is our reference angle. My favorite method is to kind of think of this quite visually. So if we were to draw a little graph here of tan 2x, we are looking for every case where our x is equal to pi over 4. So, whoa. I'm just thinking about this one. So if I draw it from here, I haven't applied the vertical squish yet. So if I apply the vertical squish on this graph, let's just take a baby tan x just in case. So if we just take tan x, it would look like this. It goes up and then it goes down, up, and then it goes down, up. And this would usually be 2 pi over here. So just to get an idea of what tan x normally looks like. So this is a normal tan x graph before any changes have been applied to it. It would have had pi in the middle. Okay, this is 0. So if we take it this from here, we could use this pi over 4 as our reference angle, and then we'd have to apply the 2x at the end. That's one way we can do it, but I think I'm going to look at it a different way. If we divide our reference angle by 2, we end up with x is equal to negative pi over 8. Okay. Now this is using the 2x one. So when it's 2x that's been squished, so we had our tan, now we have tan 2x, and all those points on the graph have been squished by a factor of 2. So 2 pi, pi, 0, and all these middle ones will be halved. They'll all be halved. So our new graph will look exactly the same, except every point, so this will still be 0 times by 2 divided by 2 doesn't make a difference. But it ends at pi now, and which is also our restriction, was 2 pi. And then in the middle here, it's going to be pi over 2. And what else do we have? So this is going to be pi over 4 over here. And this is going to be 3 pi over 4, 3/4 of the way to pi. Okay. So where does negative pi over 8 end up? Well, it's somewhere on the left here. So somewhere on the left here is negative pi over 8. And then we have to add pi over 2. Why do we have to add pi over 2? Well, usually the pi graph repeats every pi. So this distance is pi, and then the shape of the graph will repeat again. So the shape of the graph is repeating every pi amounts, which I remember as 180. But ours is being squished by a factor of 2, so the repeating will also be squished. So now it's, instead of repeating every pi or 180 degrees, it's now going to be repeating every 90 degrees, or it's going to be repeating every pi over 2 degrees in radians. Okay, let's grab another color. So we're going from our negative pi over 8, and we're plussing pi over 2 each time. And we do our certain amount of repeats, and we're going to end up somewhere over here. Oh, let's draw that a little clearer. So we go plus pi over 2. We end up on the graph somewhere over there. We plus pi over 2 again. It's going to hit the graph in somewhere over there. And we plus pi over 2 again. And that is going to be afterwards. So it's too far. This we don't need. So this one is too far. It goes past our limits of pi. Okay. So how do we work out what those exact amounts are? There's a few ways you can do it. Starting from the negative pi over 8. So if you took one of these points on the graph here, you could go from there and work backwards. So if it was from 0, negative pi over 8, then we'll go from there minus pi over 8. And then from there minus pi over 8. Let's see if that works. No, that doesn't work. Why not? Why not? Okay, so another way to the way that I've calculated it makes no sense, because this goes way too far in that direction. So I'm going to think of it another way. We just start at negative pi over 8, which is our reference angle, and plus pi over 2 each time. And that will get us, so instead of going from here to here, I'm not doing it that way. I'm going to go from here to here. Okay, each time. So you just plus pi over 2. So negative pi over 8 plus pi over 2 is our first available position. So negative pi, let me get back. Negative pi over 8 plus pi over 2. And then it will repeat. So this becomes 3 pi over 8. That's one of our options. And the other option is we plus another pi over 2. So negative pi over 8, essentially plus pi over 2, plus another pi over 2. And that will give us, that will get us to 7 pi over 8. Okay. And that should be the only answers within the range that we've been given for the interval between 0 and pi. This is the graphic way of looking at it. There's quite a few different methods to look at for this. So for this question, I'm just going to concentrate on this one. Not to forget that we have only our x's. These are our x's. So our two x options are 3 pi over 8 or 7 pi over 8. And we have to sub these back into the original equation. So we find f of 3 pi over 8, and we find f of 7 pi over 8, and solve. So, and simplify and solve. So our y will end up being, this is for our y. So we're getting some sort of xy point where our x is this in each case, and the whole thing is the y. Okay. So just looking at if I sub those into the calculator, say e to the power of 2 3 pi over 4 sine 2 3 pi over 4, for example. Okay. Oh, itchy pen. It'll give you your answers. This one will be 1 over root 2 e 3 pi over 4. And this one will be negative 1 over root 2 e 7 pi over 4. So your final points are 3 pi over 8, 1 over root 2. You should really, this I'm taking from the answer sheet. This should be rationalized generally for the exam. Taking these answers from the solution bank. Okay. See, that's a 4. So that completes a graphical method of finding for question 9A of finding turning points. This is EdExcel P3 chapter review 6, doing some differentiation questions. This question will be 9 from B to D, or at least 9B. So 9B wants f dash dash of x. So we already got f dash of x in 9A. F dash of x, I think we got in 9A. Let me just go back and check. Here it is. So f dash of x. Oh, grab that. Okay. So if we use this, obviously it was equal to 0 at the turning point. So we don't need that part. We have to derive this again. So we have a function times a function. Oh, this shouldn't have a line through it. Let's go do that. Okay. 2e 2x. Cos 2x sine 2x. So we can use the product rule. Product rule. When you have one function times another function, you name one u and the other one v. So we have, let's let 2e 2x be our u, and let sine 2x plus, this is all in a bracket, sine, not that, that might not matter. Let's see. Oopsie, that should be cos. Put the cos in front. Okay, so those are u and v. So first thing, do our first derivatives of u and v. So u dash is first derivative. When you have e to the power of x, so if you had y equals e to the power of x, it just stays the same. So dy dx would be e to the power of x. However, this one has a function inside a function. So you bring down this 2, that stays there. So everything stays the same. So for example, if we had 2 e to the power of x, it would still be 2 e to the power of x. But we've got 2 e to the power of 2x. So we need to take the first derivative of what's inside the bracket. First derivative of 2x is just see how the chain rule is affected there. So we ended up with 2 e to the power of 2x times by 2. And our v dash, well, first we have cos 2x. So cos 2x, using the same principle of the chain rule. If you had cos 2x, it would just be sine x. So if we had y equals cos x, that would just be, dy dx would just be negative sine x. Cos goes to negative sine. But we have a 2 value here, which is a function inside a function. Okay, so you'd have to times the whole thing by the first derivative of 2x, which is 2. So we end up with our v dash being negative 2, first derivative, times by sine 2x, all the same. Don't forget though, we also have to do the that was to take care of the cos, and now sine 2x becomes cos 2x. So it'll be plus 2 cos 2x. Let's just track it with the color. This one went here, and this one went here. Okay, that takes care of everything, but we haven't finished the product rule. Product rule is u dash v plus v dash u. So go from u dash to v, and we go v dash to u. Be a little bit more space, yeah. Okay. So u dash v is, well, we have, so we had 2 times 2, which is 4. So 4 e to the power of 2x times by the whole thing. So 4 e to the power of 2x times the whole thing of v. Oopsie. 4. That was because of 2 times 2. So 2 times 2 makes 4. Okay. And v dash u going the other way. So we got 2 sine 2x plus 2 cos 2x times 2. There was a negative in there somewhere. 2 e to the power of 2x. So 2 times, let's just write that all down first. 2 e to the power of 2x times by negative 2 sine 2x plus 2 cos 2x. Do one more step. 4 e to the power of 2x cos 2x plus sine 2x. Plus, yeah, that's all. I don't think there's much else we can do with that for right now. Okay. Then we just simplify this a bit. So just basically rewrote the whole thing. If we want to simplify this, there's a few ways we could do it. I'm going to try and take out a common factor of e to the power of 2x at the very least. So we take out a 2 e to the power of 2x. Let's see what happens. Let's just take out 2 e to the power of 2x. We end up with 2 times cos 2x plus sine 2x left over. And then it'll be plus minus 2 sine 2x plus 2 cos 2x. Okay. So keeping that 2 is gone. Just trying to make it look a little bit like the answer sheet. We want, what closed bracket there. Let's times this in and see what happens. E to x 2 cos 2x plus 2 sine 2x minus 2 sine 2x plus 2 cos 2x. So these two plus sine 2 sine 2x minus sine cancels out. So we have 4 cos 2x. 4 cos 2x left over times by 2 e to x. Okay, so 2 times 4 is just 8. And that gets us to our required answer, or not required. Oh, yes, it was required, our required answer. Good. So that's simplified. That's number B. B was f dash dash of x. Question C, hence or otherwise determine which turning point is the maximum. Okay, so if we had 2 turning points, one of them would be a maximum. That maximum is at the top, so that's the max. And the other, that's the other turning point would be a min. The way I remember this is the maximum point is a frowny face. Okay. And the minimum is a smiley face. So because this is a frowny face, it's going to be negative. So our second derivative is going to be negative. And because this is a smiley face, it's going to be positive. So our second derivative will be positive. And this, we can work out by subbing in the, so there was some sort of XY value here, which we got in question 9A, and there was some sort of XY value here, which we got from question 9A. So we need to sub in these X's into our second derivative here, and we will get then, we'll know if it's a positive or negative. It will give us whether we have a max or a min. So let's try, I'm just going to grab those amounts out of this. So we had our two turning points, our max and min. So they're either max or min. We don't know yet. Using the second derivative test was 3 pi over 8. Of course, you could do this graphically as well. And the other X was 7 pi over 8. So this is not non-graphically. We're using the second derivative test. So you say f dash dash of 3 pi over 8 equals, and you sub it in. So wherever you see an X, you put on this formula, you put 3 pi over 8. And I get that this one ended up being large. This one ended up being, let me just see, stick this into my calculator. This one's negative. Okay. This one has a negative answer. If the answer came to -4 square root 2 e 3 pi over 4. And the other one is, so the negative one, we go back to our little frowny face, the negative one is the max. So that means that your 3 pi over 8 is going to be your max. I think that's what they asked. Oh, which is max, which is min. So if this one's max, the other one is min. The other one should turn out to be positive. We just quickly check. So we do f dash dash of 7 pi over 8. So we sub it into the second derivative formula that we got. And that simplifies to 4 root 2 e 7 pi over 4, which is positive. That's positive. Another way you can show positive is you can say that's larger than 0. Positive one is because it's a smiley face. Positive one is the min value. Okay. So those are our two max and min values. Question D asks for the point of inflection. So point of inflection, what do we have to prove for the points of inflection? We've already got our f dash dash of x. We've already got our second derivative, so we can make use of it. For 2 marks, at the point of inflection, our second derivative is equal to 0. So we had our second derivative as 8 e2x cos 2x, and we equate that to 0 and simplify. Okay, let's see if the graphic method works for this one. So let's see. First, so well, this is something times something equals to 0. So first thing I'll check is, can these two be equal to 0? So this one doesn't look like it's going to be valid. So I'm splitting this. One of these has to be 0, either this or this. So take a look at if you have x in the exponent, this can't be real, it can't be 0. So that already takes that option out. So we only have cos 2x equal to 0. So let's draw our graph, cos 2x. And again, we're going to, like we did in question A, we're going to halve. So this would have been 2 pi. So I'm just going to show you what I do. I halve it. So 2 pi over 2. And this middle, this is a cos graph. It would have been pi. So it's pi over 2. These 2 points, this would have been, that's pi over 2. This would have been pi over 2. So it's pi over 2 times 2, which is pi over 4. And this is 3/4 of the way to pi, 3 pi over 4. So that's our cos 2x. And we want where it's equal to 0. So we want here and here. And just check that it answers the points of inflection. Those are our x's. Those are our x's. So when x is 3 pi over 4 and when x is, oh, that's a 2. Pi over 4. No, never mind. It's good. So when x is pi over 4 or when x is 3 pi over 4, those are our x's. And it's asked for the actual points of inflection. So we sub that in to the original graph, f of x. So we find f of pi over 4 and we find f of the other one, which was 3 pi over 4. Okay. And that should equal pi over 4, e pi over 2, and negative e 3 pi over 2. So just to answer the question properly, our final answer is we're going to have 2 points of inflection. That's one. And this is another one. And that concludes our question number 9. This video does B, C, and D. Okay, those are points of inflection. Good.